Okay, so last time we talked about arteries and we talked about the structure of arteries. Remember, there are three types of arteries. They're elastic, they're conducting, and then there are arterioles. And then we talked about capillaries, and there are three types of capillaries too, continuous, fenestrated, and sinusoids. And then we talked about veins. Well, veins are just divided up by size. So you can say that there are venules, and then there are small veins, and there are large veins. But again, the three different types. That's kind of what we've talked about last time. And if you have any questions about that, please ask them. Or if you want to email me with questions, you're welcome to do that too. But today what we're going to talk about is how blood moves through those blood vessels. And so it's called hemodynamics or blood flow dynamics. And so when you talk about blood flow, there's really two ways to describe blood flow, two different ways. One is the volume of flow. So volume of flow is going to have a volume unit and it's going to have a time unit. So if I were to ask you to go to your kitchen and tell me how much water was coming out of your faucet every minute in your sink, what you might do is you might, I don't know, get a gallon jug or something like that, and then you'd go over there and you'd put it under there and you'd see how long it took to fill up the gallon. So if it took 2 minutes, then what you'd say is I have 1 gallon for every 2 minutes. Or in other words, it's flowing at a half a gallon per minute. And so that's the unit that you would use. And look, it has a volume unit, just like this does, and it has a time unit, just like this does. Well, we don't usually use gallons when we're talking about blood flow. We use milliliters. But that's all it is how much blood is flowing per minute. Any questions about that? Does everybody understand what we're talking about? Okay, but there's another way to describe blood flow also, and this way has to do with how fast it's flowing, the velocity of flow. And so what we might use as an analogy here is your car. So if you think about your car going down the road, it has a certain velocity, it has a certain speed. And as it moves down there, if you look on your dash somewhere, you're going to see how fast your car is going. And look, it's going to be in something like miles per hour. In other words, it doesn't have a volume unit, it has a distance unit. A distance unit, and then it has a time unit. A time unit. So it doesn't tell us how much is flowing. What it does is it tells us how fast it's flowing. In other words, it could be a lot that's flowing, or it could be a very small amount that's flowing, but they could be flowing at the same rate, the same speed. So two different ways to describe blood flow. Any questions about either of these? Does everybody make sense to them? Well, they're both important. So look, what if we were to have some sort of, I don't know, some sort of disaster? You know, there's an earthquake or a hurricane or something. And look, there's 500 people that are stranded here and they have no food and they have no water. So we want to deliver that to them. Well, look, if you look at this ship can carry a lot of water. Look, it can carry 100,000 units of water. Look at that one, it can only carry 10,000 units of water. So which of these do you think you would use if you want to send water to these 500 people? Anybody have a guess? What would you do? Which one? Would you use the big one or would you use the smaller one? Well, Daryl says the big one. That's because, look, there's a lot more water and you can fill a lot more things. But look at this. It takes 10 days for this to get there. How long can you live without water? Can you live without water for 10 days? No, you cannot live without water for 10 days. So if I just relied on this one, these people would all be dead by the time I got there, or at least they would be drinking water that was unsafe. But look, this other ship, even though it can't carry as much water, look, it only takes 1 day to get there. And so I can't supply 500 people for very long, but at least they're not going to die of thirst. And so look how both these things are important. So volume is definitely important because it has to do with how much is being delivered. But velocity is also very important because it has to do with how fast it gets there. So let's forget about people for a second and let's think of cells. So we have cells in our body and we're wanting to deliver oxygen and nutrients to them. Well, if we just use this, yes, that's a lot of oxygen, that's a lot of nutrients. But by the time it gets there, those cells might have starved. They might have been to the point where they're going to be actually hurt or damaged. This one doesn't carry nearly as much and it's not going to last as long, but it's going to get there much, much faster. So again, both are important. So when we describe these two different ways of blood flowing, one of these is volume and one of these is velocity. And they're both equally important. Does that make sense to everyone? Any questions about it? Anybody else? We only have 4 people in here today, including me, so it's not a very big group, but maybe they'll watch this later on the recording. But anyway, let's go on. So we're going to look at both of these ways of talking about blood flow. Let's look at volume first. So remember volume, we have to have a volume unit and we have to have a time unit. And so usually what we're going to do is milliliters per minute. Milliliters per minute. So if you think about blood flowing around, remember it's the heart that's pumping it. So the heart pumps to the lungs, it comes back to the heart, it pumps to the tissues. And so the amount of blood coming out of the heart, everybody should remember this from last time, is called the cardiac output. And so the cardiac output is going to be the total volume. That's all we have, so that's all it can be. But remember, when it comes out of the heart, it splits up. Some blood goes this way, some blood goes this way, some blood goes this way, some blood goes this way. Could be your head, it could be your arms, it could be your stomach. And so that cardiac output is this total amount. And so when we look at these individual things, we're going to see that it varies widely. So when we talk cardiac output, that's the total blood flow. And it is in milliliters per minute. And remember we said on the average, it's about 5,000 milliliters per minute or 5 liters per minute. But of all of that, that's what we have total. Some of that has to go to your head. Some of that has to go to the heart. Some of that has to go to the stomach. Some of it has to go to your muscles. And so we're not so interested now in this total, but we're interested in the amount that goes to individual places. And so if we look at that, you can see how different it is depending on what our activity is. So if you look at the volume of flow to these organs, this is what it is at rest. So at rest, look, most of the blood goes to places like your liver and your kidneys. Look, that's 46% right there. If we add the heart, that's 51%. If you add the brain, look what it is. But the second you start exercising, these organs don't get nearly as much blood anymore. These are the organs that are going to get blood. So look what happens during exercise. Brain's down, heart goes down, liver goes down, kidneys go down. All of these go down except this one, which goes way up. Does that make sense? So when we look at it, we're still only talking about the cardiac output. Now, cardiac output at rest, remember, is about 5,000. That number is going to go up when you start exercising. It might go up, I don't know, let's say it goes up to 10,000. So look, 20% of 5,000 versus 87% of 10,000. This number goes way, way, way up. Any questions about that? Everybody get it? So let's look at how can we change the blood flow. We changed it dramatically, but how do we change it? So let's look at the factors that affect blood flow. Well, the easiest way to do this is to think about this in terms of an equation. So if we look at this equation, we want to talk about blood flow. And these are the things that are going to affect it. The pressure, which I push it with, that's the initial pressure. That's the pushing pressure. The final pressure is the pressure resisting it. It's pushing backwards. And then finally, the resistance as it moves through the blood vessels. So those are the things that are going to change this flow. So let's look at these. Remember we talked about afterload already. That's the afterload right there. And that is this. So look, here's the final pressure here. And here's the initial pressure here. So it's not just this number, it's this number minus this number. That's what's going to determine what causes the flow. So when we look at it, initial pressure minus final pressure, or another way to say that is the difference in pressure over the peripheral resistance. Does everybody understand this pressure thing here? This is initial pressure, and this is final pressure. So what if our initial pressure here is 120? But this pressure in here, remember, is, I don't know, let's say it's 80. So it's not this pressure, it's not this pressure. It's that minus that is what's going to make it move. So 40 is what's making it move. Look at this. This person has high blood pressure. Look, they have a high blood pressure. This is not 80. It's 110. So look, if I pump with the same pressure here, is as much blood going to flow? Remember over there we said 40 was pushing it. How much is pushing it here? 120 minus 110. It's only 10. You think as much blood is going to move? Yes? No? No, and that's one of the problems with high blood pressure, is that at a lower pressure down here, at a normal pressure down here, we don't push very much blood. So if we want the same amount of blood to go, remember we had 40 over there, this number can't be 120. What is it going to have to be in order to wind up with a net of 40? This is going to have to be 160, which means that person's heart is working much, much harder than someone who doesn't have high blood pressure. So, initial pressure minus final pressure. That is one of them. Let's look at this one. So this one, how much blood is it going to move? A little or a lot? How are we going to figure it out? We take 120, and what are we going to subtract from it? 118. How much blood do you think is going to move? There's only a net pressure of 2. Remember what our equation is? Here's our equation right here. So in other words, we're going to put 2 in there. How much blood is going to move? Nothing at all, really. Does that make sense to everyone? So this one, a lot more blood moves than this one. Any questions about it? So remember, it's this difference in pressure, initial pressure minus the final pressure. And the higher the difference, the greater the flow. So what if you start exercising and you get in really good shape and you drop this number down? So someone who's in really good shape, their blood pressure is, I don't know, 110 over maybe 75 or 78. Look what happened. With the same work, the heart is going to be able to make more blood move. You're going to get more blood moving with the same amount of work. And so we're not going to overwork or overtax the heart as much as we would something like this, because this is not going to make blood move at all. So this number is going to have to get much, much, much higher. Any questions? The other thing that affects blood flow is peripheral resistance. So peripheral resistance is the resistance that the blood encounters as it flows through the blood vessels. In other words, resistance pushes backwards. So if resistance goes up, flow goes down. Look, it's an inverse relationship. So if this number gets bigger, look, we're dividing it. And so that number is going to get smaller. So let's look at peripheral resistance. So remember what it is the opposition to flow. It's what opposes flow. Remember, it's this inverse relationship. If resistance goes up, flow goes down. If resistance goes down, flow goes up. Well, there are 3 factors that are most important when we talk about peripheral resistance. And here they are right here. So one is the length of the blood vessels. Another one is how thick or viscous the blood is. And the last one then is the diameter or radius of the blood vessel. Well, those are kind of hard to sort of imagine or think about. So let's do it a different way. Let's forget about this for a second. And let's go to McDonald's. I'm thirsty. So we're all going to go, and I'm going to buy every one of you a nice big soda so we can have a nice soda together. Make sense? What kind of soda does everyone like? I'm taking orders. How many people want a Coke? Anybody? How many people want a Diet Coke? How many people want, I don't know, Sprite? But if you think about all of these, they're pretty much the same, right? There's except for the taste. But look, when we get to McDonald's, remember we can't go inside, so we're going to have to go through the drive-through. And there's our nice drive-through person, and she's got our Cokes here. But look, when we get to McDonald's, this guy is in the drive-through. And look, he's going to play a trick on us. And so what happens is when we get back to where we're going and we look at the straws, look what we got. One person got a short straw, little straw, big straw. In fact, one person got this straw, and one person got this straw, and one person got this straw. Well, remember, these are all sodas. It's the same volume. Everything's the same except the length of the straw. So if we all take a drink from this, we're all going to suck on the straw, and we're going to suck on the straw with the same pressure, the same sucking pressure, the same negative pressure. Do you think we're all going to get the same amount of liquid flowing into our mouth? We won't. Who do you think is going to get the biggest flow? Anybody want to guess? Daryl's right. It's the shortest straw. In other words, we're going to wind up with a higher flow rate. More fluid is going to come out of here than what comes out of here. And what comes out of here. Look at this. Here's another thing. What if I were to do this? I'm going to go home. Here's my house. And I'm going to water my grass. So look, there's a faucet here on the side of my house. And here's where I want to water over here. So here's my sprinkler. And I'm going to take a hose and I'm going to hook to the sprinkler. And look, this hose is about 50 feet long. That's how long the hose is. So I'm going to turn the water on. And here comes the water. It comes spewing out and it's going to water my grass. And look, this is how far it goes. Look how much of my grass was watered with this particular sprinkler. But 2 days later, a couple of days later, I'm going to do the exact same thing again. So again, here's my house. Nothing's changed. There's my thing, and here's the faucet. But when I look at the hose, there's something wrong with it. I don't know, a rat has chewed a hole in it. So that hose is no good anymore. And so the only other hose I have without going and buying another one is not 50 feet long. This one's 75 feet long. So look, I'm going to have to like make it roll like this or whatever, but I'm still going to keep my sprinkler in the same place. I'm going to hook it up. Guess what happens? I'm going to turn the faucet on exactly the same as I did the day before or 2 days before. But this is what's going to happen. The water's going to come out like this. Only this much of my grass is going to get watered. Why do you think that is? What's the only difference here? Same pressure here as here, same sprinkler, same diameter hose. The only difference is the length. In other words, if I increase the length, I decrease the flow, just like I did with those straws. So the question is, why? What happens that makes me, or makes this happen? Why? What's going on? Anybody want to guess? It is a longer distance to travel. That's true, 75 feet. But what has that got to do with anything? What's going on that makes this happen? Why? Why does length, this length versus this length, why does less come out here and more come out here? Now, we're not talking about how long it takes to get there. We're not talking about that. We're talking about the amount that comes out, the volume of flow. When I measure it here, this might be 5 milliliters per minute. This would probably be 10 millimeters per minute coming out of it with the same pressure. What's going on? Why is this happening? Same thing we did with our drink. Remember, here's our drink. Shortest straw, most fluid, most liquid comes out. Why? Well, here's why. Let's look at the hose from the other end. So look at it from this direction. And here's the hose going this way. And here's the hose too, same diameter. This one's only this far. So as the fluid goes through here, whether it's water or where it's blood, when it gets near the edge of the tube, it rubs on the tube. Everybody rub your hands together. What happens when you rub your hands together? They get hot. Why? What's making your hands get hot? Friction. So look, there's friction all along here. And friction slows things down. It makes it less likely to move. This one only has this much friction because it's only that long. There's less friction, less resistance. And so if there's less resistance, then the flow goes up. So the relationship here is that if I increase the length, what happens if I increase the length? I'm going to increase the friction. And if I increase the friction, what's going to happen to flow? Flow is going to go down. So the relationship here is it's an inverse relationship. If I increase the length, I decrease the flow. Does that make sense to everyone? Any questions about it? So let's go back to what we were looking at. So, remember we all had drinks, and there they are. And again, this one is going to have the least flow. Can someone send me an attached net to the Wiggers diagram? I sent it by email. I also posted it on eCampus. Did you not get the email? Let's see if I can resend it. I'll tell you what, I'll send it to you. I can't get out of this right now. But anyway, we're going to have the most flow here, the least flow here. And so the relationship is, it's an inverse relationship. So look at this. This one's exaggerated, but look, all along here, there's going to be friction. Look how much friction there is all along here compared to this one. And everywhere there's friction, it's pulling backwards or dragging backwards on the fluid. And as it drags back, then the fluid does not flow. And so if we compare this to blood vessels, think about this. You think the blood vessels all the way to your leg are as the same distance as those, say, I don't know, to your lungs. So the lungs, remember, it's a short distance. We don't need much pressure. So if we go back to my other analogy, so remember, I should have done this with a blank, but anyway, there's my house, and there's the little sprinkler, and it's sprinkling, and I only get this much. Remember the day before, when I did it, I got a lot more. This is our 50 foot, this is our 75 foot. So I'm not happy with how much grass is being watered, but I don't have another hose. That's the only hose I got. So what could I do over here to make this go back to like that? What could I do? What can I do at the faucet? What else affects flow besides resistance? Remember, it's the net pressure. So what could I do at my faucet to make more water come out? I could increase the pressure. So what could I do at my heart to make blood flow to my legs and my arms the same way that it flows to my lungs? What could I do to equalize the pressure? I could increase, or not equalize the pressure, equalize the flow. I could increase the pressure. Do you remember which side of the heart pumps to the arms and the legs? Which side? Which side pumps to the arms and the legs? The left. Which side pumps to the lungs? The right. Do they pump with equal pressures? No, remember this one's like 120. This one's like 40. Well, the reason why, at least one of the reasons why, is because the distance that we're pumping. Does it make sense to everyone? So if I want to pump equal volumes, I've got to use more pressure over here. Just like if I want to pump, sprinkle equal volumes, I got to use more pressure over here because this is a lot longer, and less pressure here. Any questions about that? So here's our relationship. Remember, it's an inverse relationship. Oh, this is resistance. Flow. It's an inverse relationship. So let's go back to McDonald's. I'm not very happy because we got these weird straws. But look, there's that same guy there again. But we get our drinks and we come back and we look, and look, all our straws are just fine. Look, they're all the same length, everything's fine. But look at this. These are not the same things. Look, that's tea. That's some sort of Slurpee. Look, that's a smoothie. And that's some sort of coffee or something like that. So our straws are the same length. That's okay. But now, what's different? How is tea different from a smoothie? What's different about those two? Or this one or this one? It's the thickness. It's the viscosity. The viscosity is the density, the thickness of the liquid. And look at these. If we look at these, look, that flows much faster than something that has a higher viscosity. So if I look at these two, I can see there's a relationship between viscosity and flow. If I increase the viscosity, look at it. What happens to flow? It goes down. It's again this inverse relationship because there is more resistance. There's more resistance to flow if it's thicker. So if I want to get the same amount of fluid to go through here and here, remember the length of the straws are the same. What am I going to have to do when I suck on these? What's going to have to happen with pressures? Can I use the same pressure for this as I do for this or this? So if I increase the viscosity, I'm going to have to increase the pressure. Does that make sense? So if my blood were to get thicker, instead of my blood being like this, my blood is like this. Look, a smoothie's got like ice cream stuff in it, and so it's very thick. So if I want the same amount of blood to go to my leg with this blood, and the same amount of blood to go to my leg with this, I'm gonna have to pump harder. Make sense? So, again, there's a relationship here. If I increase the viscosity, look what happens to flow. Flow goes down. So there's more resistance with viscosity. So if I increase the viscosity, I increase the resistance. And remember, if I increase the resistance, I decrease the flow. So we're going to go back again. Wow, I'm getting tired of this. But anyway, we're going to go back, and there he is again. And look, when we get our drinks this time, oh my God, can't they do anything right? But look at these straws. Look, they're the same length. Length is the same. We all got sodas, that's okay. But now, look at these things. They're different in diameter. Which one of these, if we suck on them with the same pressure, same everything, are we going to get the same amount of liquid? Which one's going to give us the most liquid? Is it this one? Yeah, it's going to be the biggest one. So what changed here was the radius. And so if we look at the radius, you can see what a huge difference it has on flow. So look, here's exactly the same pressure. It's a constant pressure in all three of these pipes. Same pressure. But look what happens when I get here versus here versus here. So look at the radius or the diameter of that opening. And look at the radius or diameter of that opening. And it's easy to see if I increase the radius, resistance is going to go down. And when resistance goes down, flow is going to go up. Does it make sense? So what if this were the heart and these were blood vessels? Remember, we can change the size of blood vessels. Do you remember how we do it with arteries? Remember, there's that layer of muscle in there, and we can make that muscle contract. What would you call that? vasoconstriction, or we can make that muscle relax. And remember, that's vasodilation. And so look what happens when we vasoconstrict some vessels and vasodilate some vessels. We can change where the blood is going. So remember what happened? We were talking about exercising. So when we were exercising, remember what happened to the brain, the liver, the kidneys, all of those. That's what happened. And this is what happened with muscles. So we could choose where to send the most blood or the least amount of blood. Does it make sense? Any questions? So again, there's a relationship. So if we increase the radius or diameter, we're going to decrease the resistance. And if we decrease the resistance, remember, we're going to increase the flow. So the easiest way to see this is to put these things in an equation. And that's exactly what we're going to do. So we're going to put them in an equation. Length, viscosity, and radius. We're going to put them into an equation. And these are the things that are going to affect where the blood is going, how much each organ is getting. Well, again, the factors affecting resistance are length. So if we increase the length, what happened to resistance? Do you remember? Does resistance go up or down? It goes up. If resistance goes up, it needs to go in the top part of the equation. Remember viscosity? If I increase the viscosity, what happens to resistance? Does it go up or go down? It goes up. If it goes up, it needs to be in the top part of the equation. But what happens if I increase the radius, the diameter? What happens to flow? What happens to resistance? Resistance does what? It goes down. And if it goes down, I'm going to put it in the bottom of the equation. So when we look at this equation, it's very, very simple. Peripheral resistance is equal to length times viscosity divided by radius. But it won't work. It won't work unless we put constants in it. All a constant is kind of a fudge factor. It just makes the equation work. Why are they called constants? Yeah, they never change, exactly. So that number 8 is always going to be there. That pi is always going to be there. They're never going to change. And when you talk about the variables in the equation, these are constants. They don't change. They're not variables. So we don't really have to think about them. Remember, they're just fudge factors to make the number work. Again, the only variables are length, viscosity, and radius. But even then, when we put these constants in here and we try to do the equation, it won't work either. And the reason it won't work is because these three factors don't contribute equally. In other words, one of these has more of an effect on this resistance than the other two. And the one that has more of an effect is radius. And when we figure out how much more of an effect it has, we find out we have to raise radius to the 4th power in order to make it work. But when we do that, it works. So we have length, we have viscosity, and we have radius. But again, we have to raise this one to the 4th power. So the question is, do they all have an effect on the same effect on resistance? Same effect on flow? They don't. Radius has got a much bigger effect. And look, here's an example of that. If we were to put ones in our equation, let's go back to our equation. Let's say length equals 1, viscosity equals 1, and radius equals 1. And we're going to forget about these because they're constants. We're not going to worry about them. So look, I'm going to put a 1 here, a 1 here, and a 1 here. But remember, this is raised to the 4th power. So what's 1 times 1 equals 1, right? And what's 1 times 1 times 1 times 1? Because that's what happens when you raise it to the 4th power. But what is 1 times 1 times 1 times 1? It's still 1, right? So in other words, our resistance is 1 divided by 1. Our resistance equals 1. Look what happens if we changed everything. A little bit of time, though. So I'm going to change length to 2. So this number's not 1 anymore. It's 2. So look, 2 times 1 is 2. 1 times 1 times 1 times 1 is still 1, right? So that number equals 2. Makes sense? Let's fix this one back to 1 again, and now change this to 2. So viscosity is going to be 2. Look, we're going to get the exact same thing. 1 times 2 is 2, divided by 1 times 1 times 1 times 1, still going to be 2. But look what happens if we change radius to 2. So we're going to put this back to 1, put this back to 1, but now this is 2. Look, it's 2 times 2 times 2 times 2. What is 2 times 2 times 2 times 2? Anybody know? Yeah, so look, it's 16. Look what happened. It went from, something's frozen. It went from 1, that's what we got. Remember, that went to 2, everything went to 2, but this one times it went from 1 to 1/16. Look at the huge difference. And what if we just were to change everything to 3? If we change this to 3, it changed that to 3, we would get 3, and then we did it again, we'd get 3. But if we change this to 3, look, it's going to be 3 times 3 times 3 times 3. What is 3 times 3 times 3 times 3? Anybody know? It's 81. So look, if I change from 1 to 2, or if I change it to 3, this is going to go from 1 to 1 over 81. So because this varies with that 4th power, we have a huge, huge difference in how much it affects. There's a much bigger effect on resistance that radius has versus the others. If we increase the radius from 1 to 2, we're going to change it by a factor of 16. If we go from 1 to 3, we're going to change it by a factor of 81. That doesn't happen with these others. Does that make sense? So we're not really interested in resistance, though. We're interested in flow. Remember, they're opposites. If resistance goes up, flow goes down. If resistance goes down, flow goes up. In other words, there's this inverse relationship. So if I really want to know what this equation is, I'm going to have to flip it upside down, because remember, our original equation was this. So flow equals the difference in pressure divided by peripheral resistance. Here's peripheral resistance. We're going to plug that in. And then, because this is on top of this and this under there, we're going to have to flip it upside down. And so we're going to wind up with an equation for flow. And here is the equation for flow. Look, it doesn't have anything new in it. There's the pressure. Peripheral resistance is these things. So here's the equation for flow. And this is what I want you to write down on your sheet if you haven't already written it down. And I want you to look at it. A lot of people hate equations, and I understand that. But equations are the easiest way to see everything all at once. So look, without knowing anything about flow, I can look at this equation and I can say, if this number goes up, what's going to happen to flow? It's going to go up. So if I increase the difference in pressure, in other words, there's a bigger push versus how much is pushing back, I'm going to increase flow. But look, I could change one of these others too. I can't change radius, that's a constant. Pi, that's a constant. I can change length though. So what happens if I increase the length? What happens to flow? It's in the bottom part of the equation, so flow is going to go down. Here's this other one. What happens if I increase viscosity? If I increase viscosity, flow is going to go down because it's in the bottom of the equation. And then the last one is, what happens if I increase radius? So radius is in the top of the equation. So if I increase radius, flow is going to go up. Make sense? So you tell me, what are the ways that I can increase flow? I want more blood to go to my legs. So here's the heart, right here in my chest. And I want more blood to go all the way down here. What are the ways I can do it? I want to increase flow. That's all I want to do. So how do I increase flow? Well, the only things that are in this equation are the difference in pressure, the length, the viscosity, and the radius. So tell me, how can I increase flow? What are the ways? I can increase the difference in pressure. Remember, there's two pressures. There is an initial pressure and there's a final pressure. So I can increase initial pressure or decrease final pressure. What else? I can increase the radius. I can decrease the length. And I can decrease the viscosity. And those are the only ways to do it. Because that's all that's in the equation. There they are. So if I want to increase blood flow to a particular organ, I don't know, the liver, how do I do it? These are the only ways to do it. Does that make sense to everyone? Any questions about it? So this is also what you should write down on that sheet. Or just you can always come back to this PowerPoint. But these are the only ways to increase flow. But here's another question. Are they all going to have an equal effect on flow? Is this and this and this and this and this all going to have an equal effect on flow? Well, the easiest way to look at that is to go back and look at our equation. Look, that's not raised to any power. That's not raised to any power. That's not raised to any power. But this one is raised to the 4th power. So, are they all going to have an equal effect on blood flow? No, they're not. They're not. Radius is going to have a much bigger effect on flow because it raises or raises with the 4th power. So if I want to change flow, and again, let's say I want to change it so that more blood goes to my feet. Of all of the ways I can increase flow, which one of these is going to give me the biggest bang for my buck? Can I really change the length? I want to go from here to here. I want to go that far. So I really can't change the length. It's hard to change the viscosity of blood. You have to either drink more water or you have to pee out more water. It's going to take time. So that's not a good way to do it. The only ways I can do it are these ways right here. I can increase the initial pressure. In other words, I can increase how much blood the heart is pumping. It's a little bit harder to decrease the final pressure. That's blood pressure. But you can. But of all the ways to do it, the easiest way is to change the radius. And how do you change the radius of a blood vessel? What do you call that? What do you call it when a blood vessel gets smaller? Vasoconstriction. And what do you call it when a blood vessel gets bigger in diameter? Vasodilation. So the easiest and best way for me to make more blood flow down to my feet and legs or wherever I want to go, the liver or whatever, let's say the liver, is to vasodilate the blood vessels to the liver. I'm going to open them up. I'm going to go from this to this. And lots more blood is going to flow. By the same token, what if I want to decrease blood flow? Well, I'm going to do the opposite of these. I'm going to decrease this or increase this, increase this, increase this, or decrease that. But again, they're not going to have an equal effect. The one that's going to have the most effect is radius. So remember that picture I showed you before with the pipes? Here's the exact same picture, except these are arteries. They're arteries. So there's the diameter, the radius, and there's the diameter, the radius, and there's the diameter. The lengths are the same. The fluid going through it is the same. And the pressure is the same. But look at the difference in the amount of blood that flows to a particular organ. You see a huge increase in the amount of blood flowing through the blood vessels when you increase the diameter or the radius. Does it make sense? Any questions? So look what happens if we decrease the radius or the diameter. Well, we can do that intentionally with vasoconstriction, but it could also happen when you get occlusion. In other words, there are plaques building up in an artery. So look, here is a healthy artery. Look, it's got no plaques. And there's the radius, the diameter right there. And look what happens. If the pressure is 120, which is a normal pressure for a heart, look what the flow is going to be. It's going to be 100. That's with 0% occlusion. But look, if we add just a little bit of plaque inside this artery, just a little bit, look, it's only 20% occluded. Look what happens if the pressure is the same. Flow drops down to 41. And if I want to bring that flow back up, remember the only way I can do that is to increase the pressure. So look, if I want to bring it back to this normal flow rate, look at what I have to have as a pressure. Not 120, 293. In other words, the heart has to pump. That pressure, the systolic pressure, has to be 293 to get the same amount of blood to flow through this artery as this one. And look at this, it's even worse. What happens if you have a 50% occlusion? Well, look, there's still blood going through there, but if the heart rate or the blood pressure is 120, look, this is how much blood goes through there. And if I want to bring that back up to normal, look at what the heart has to produce. 1920 millimeters of mercury. And no heart can do that. No heart can do it. It's impossible. It means that whatever this is going to, the organ that this is going to is going to be deprived of oxygen and nutrients. And then look at this one. What if there's an 80% occlusion? Look at that. An 80% occlusion at 120, this is what flows through there. Look at that compared to that. And if I want to bring this back up to normal, look at what heart pressure I would have to produce. The heart would have to produce 75,000 millimeters of mercury pressure. And that is just totally 100% impossible. And so whatever organ this is going to suffer like crazy. Well, remember the arteries around the heart, the coronary arteries? Well, coronary arteries are subject to occlusion. So you hear about people who have a 40% occlusion, a 50% occlusion, an 80% occlusion. That's the blood going to the heart wall. That's the part that's going to the muscle of the heart. In other words, that heart is being deprived of oxygen and nutrients. And if you deprive it enough, that's when you get something like an infarction, a myocardial infarct. Sense? Any questions? So that's one way to talk about blood flow. That's volume. But there's another way to talk about blood flow, remember, and this is how fast it's flowing. How fast it's flowing. And that's called velocity. Well, if you look at velocity, it changes as it moves through the circulatory system. As it's coming out of the heart, blood moves very, very, very fast. But as you go through the system, it changes a lot. Depends on where you are, what the velocity is. What affects velocity more than anything is called the total cross-sectional diameter. In other words, if I look at a blood vessel, that's cross-sectional diameter. But what if I don't have one of them? What if I've got two? So I have to add this and this to get the total, because blood's flowing through both of them. Or if I've got 8, I'm going to have to add all of these to get the total. Does that make sense? So here's a pretty good analogy for this. And that is to think about how water flows in a river versus a lake. So look, the same amount of water is entering as is leaving, the same amount. So the volume is exactly the same. We're not talking about volume. We're talking about how quickly it flows through the system. Velocity. Well, if I look at this right here, the total cross-sectional diameter here is this much. But if I look here, the total cross-sectional diameter is this much. And if I look back over here, the total cross-sectional diameter is this much. So look, there's a relationship here. If I increase the total cross-sectional diameter, look what happens. The water, the blood, the fluid slows down. So when the total cross-sectional diameter is small, the fluid flows very, very fast. But when the total cross-sectional diameter is large, the fluid flows very slow. But look, when I got back over here, it got small again. And so the fluid has to flow fast again. So I don't know how many of you are interested in things like canoeing or kayaking, but if you get in a canoe and you were to ride down this river here, you probably would not have to paddle very much at all. You would be going very, very fast. You'd just be zooming down this river. But when you got into this lake, because this total cross-sectional diameter is so much bigger, the water's going to slow down. And your canoe is going to slow down too. And it's going to take you, if you don't paddle, hours to get across this lake because the water is flowing so slowly. But look what happens when you get over here. It's going to zoom again. Look at this. You can even see it. So this is a river right here, but it's a wide river. And wide rivers flow slowly. But look, as it goes through this narrow passage, the same amount of water has to get through this smaller space. So it has to speed up. It has to go very, very fast. Does it make sense? Any questions? You can see it here. So, small total cross-sectional diameter, fast. Large total cross-sectional diameter, slow. Well, that's true if I have one big open space like this, or if I have all these individual spaces like this, plus this, plus this, plus this, because we're talking the total cross-sectional diameter, not the cross-sectional diameter of one thing. If I look here, the total is just this right here. And I don't know what number that is, but let's say it's 10. But look, if I look from here to here to here, the total is probably 100. Because that's 5, and that's 5, and that's 5, and that's 5, and that's 5. Let's say there are 20 of them. It doesn't look like they are. But anyway, it's a bunch more. But when I get back here, the total cross-sectional diameter is 10. So when blood flows through blood vessels, it's the exact same way. So look, blood comes out of the heart, and the first vessel it flows into on the left side is the aorta. Well, the aorta is big. It's the very largest blood vessel in your whole body. It's about 1 inch in diameter. But how many aortas does a person have? They have 1. So if I want to figure out the total cross-sectional diameter, I have to multiply those two. So look, 1 times 1 equals 1. So the total cross-sectional diameter for this area is 1. But then blood's going to go from the aorta into the elastic arteries. Remember, these are the arteries like the subclavians and the iliacs and places like that. Well, I don't know exactly how many of them there are, but let's say there are 10 of them. I also don't know exactly how big they are, but I know they're smaller than the aorta, so let's say they're a 1/2 inch in diameter. So look, they got smaller, but because there's more of them, the total cross-sectional diameter goes up. And then I'm going to get to the even smaller arteries. There's a bunch of these. I don't know exactly, but let's say there's 100 of them. And they're much smaller than the aorta. Look, they're only 1/4 inch. But because there's so many of them, the total cross-sectional diameter here goes up again. And then we're going to go from there to the arterioles and then to the capillaries. Remember, capillaries are tiny, 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 tiny. Remember, they're only about 8 microns in diameter. That's about 8 microns. It's not a big vessel. Compared to that, they're tiny. These are microscopic. But remember, we have so many of these. There's about 3.5 billion of these. And if I multiply 3.5 billion times this, look what happens to the total cross-sectional diameter. It goes way, way up. Does this part make sense to everyone? But then look what's going to happen. We're going to go into the veins. So veins are bigger than capillaries. Look, they go from being this tiny little thing, they're back to 1/4 inch. But we don't have anywhere near as many veins as we do capillaries. We only have this number. So now we're going to have to multiply. Even though they're bigger, there are fewer of them. And so we're going to wind up with a smaller total cross-sectional diameter. And we're going to keep going into bigger and bigger veins until finally we get to the 2 largest veins in your body. Remember, one's on the top of the heart, one's on the bottom of the heart. They're the inferior and superior vena cava. There are only 2 of these, but they're huge. They're not quite as big as the aorta, but they're almost. They're about 3/4 inch. But look, we only have 2 of them. So if I multiply 2 times 3/4 inch, I get 1.5. So look what happened here. I went from a small total cross-sectional diameter to a large total cross-sectional diameter, back to a small total cross-sectional diameter. And look, it looks just like this. Look, it looks just like this. Small total cross-sectional diameter. Large total cross-sectional diameter. Small total cross-sectional diameter. And remember what happens when fluid flows through a small? It's fast. When it flows through large, it's slow. When it flows through small again, it's fast. And so look, here it's small. So blood is flowing very, very fast. But here, it's large. So blood is flowing very, very slow. And then here it got small again. And so, again, it's flowing fast. Does it make sense? So if I look at this, here is the total cross-sectional diameter. If I just graph it, so I'm going to put these numbers over here. Right here, there's 1. And then over here is 5. And then 25. And then here is, whatever that is, 1,000. Back down to 1.5. That's the total cross-sectional diameter. Here's the aorta. Here's the capillaries. And here's the vena cava. And remember, when total cross-sectional diameter is small, velocity is fast. When total cross-sectional diameter is big, velocity is slow. And then when total cross-sectional diameter is small again, velocity speeds back up again. So if I compare the total cross-sectional diameter with velocity, it looks like this. Small total cross-sectional diameter, big velocity, very fast. Large total cross-sectional diameter, very, very slow. And then back here, another small total cross-sectional diameter, it speeds back up again. So what are the vessels that go here? This is the aorta. These are the capillaries. And these are the vena cava. So in the aorta, it's very fast. In the capillaries, it's very slow. In the vena cava, it speeds back up again. Does that make sense? Looks like this. There's the big blood vessels. There's the capillaries. And there's the vena cava. So remember, it's not the size of one blood vessel, it's the total. So here, there's only one to add up. The total is small. But here, look, I'm adding this plus this plus this plus this plus this plus this plus this to get the total. The total is large. Here, again, there's only one, so the total is small. And then that is exactly what we saw before. So here's a fairly nice summary slide. It shows everything on one slide. So arteries, 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 capillaries, 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 veins, veins, veins. And then here you can see what happens to the speed as it goes up and down. Here it's high, here it's very low, and here it's high again. Any questions? So if we graph it, remember it looks like this. You might be tempted to think this has something to do with pressure, because over here's the heart. And you'd think that because the heart is pumping the blood, then it's going to speed up. And that's true. But if it were pressure, why would it speed back up again? Pressure doesn't do that. Look what happens with pressure. Here's the heart. Pressure is high at the heart, but look, it keeps getting lower and lower and lower the further you get away from the heart. It doesn't look like that graph. If this was due to pressure, these two graphs would look the same. But this isn't. That goes up while that's going down. So it's not a function of pressure. It's a function of this total cross-sectional diameter. And again, if I increase the total cross-sectional diameter, I decrease the velocity. So, here's another good slide. And if I were you, I would memorize, or not memorize, but completely be able to understand this slide. And so I might ask you, what is the total cross-sectional diameter of capillaries? And I would expect you to be able to figure it out. So if I asked you to say the average total cross-sectional diameter, so what you're going to do, there's the beginning of the capillaries, there's the end, right here is the middle, that's where the average is. You're going to come up, and what you're going to do is you're going to look over here and see what it is. So what is the answer for the total cross-sectional diameter of capillaries? Average. It's, I don't know, say 4,800. Everybody see that? So what if I didn't ask you that? What if I ask you the question, what is the velocity of flow in the arterioles? So velocity of flow, am I going to use this graph? No, I'm not going to use that graph. Am I going to use that one? No, I'm not going to use that one. I'm going to use that one. No, look, that's diameter. That's blood pressure. I'm going to use this graph. And I want to know in the arterioles. So here are the arterioles right here. And so what I'm going to do is find the center of that, and I'm going to come up, and I'm going to draw a line over from that. And so the answer is, I don't know, 3.5. Does it make sense? And there's a ton of questions that I could ask you from these graphs. What is the average vessel diameter of the veins? So same thing, you'd find the veins, but you don't want the ends, you want the middle part, and you're going to come up here. There's what the average diameter of the veins is, whatever that number is right there. Any questions about it? So you figure out this question for me. What is the average blood pressure in the capillaries? So first you got to choose which one of these you're going to use. And then you got to figure out what is the average blood pressure in the capillaries. See if you can figure it out. What answer do you get? Looks like only one person's paying attention. Anybody else know how to do it? So again, you have to choose the right graph. I asked for blood pressure. So the only graph that has anything to do with blood pressure is this one. And I asked for capillaries. So here's capillaries right here. So I'm going to pick the center line, and I'm going to go up right there. And I'm going to draw a line straight over from there. And whatever that number is, that's going to be I don't know, let's say it's about that. And that's exactly what Daryl got. So it's 25 millimeters of mercury. That's what the average blood pressure is in the capillaries. So one of the things you're supposed to be able to get out of this class is to be able to interpret graphs. You're going to use these things your whole life if you stay in any kind of healthcare field. You're going to have data. You're going to have graphs, and graphs are just a visual way of presenting data. So there's that. Well, remember we said blood pressure kept going down, so it does. Look at it. And so when you get to blood pressure in the veins, it is so low that blood is hardly moving at all. And so if we rely just on the pressure to make blood go through the veins, it wouldn't move. And so veins have helpers to make the blood flow. There's 3 helpers. One is that every time you take a breath, we sort of suck blood toward the heart. In other words, what happens when you take a breath is you create a negative pressure in your chest. And it's just like sucking on a straw. So if we suck on a straw, like we did at McDonald's, what we're creating is negative pressure in our mouth. That negative pressure also is what happens when you take a breath to make air flow in your lungs. Well, not only does it make air flow, it also sucks blood. So it sucks blood toward the chest. So that's one helper. Another helper is skeletal muscles. Skeletal muscles. If you look at skeletal muscles, they squeeze the veins. Look, veins are embedded inside skeletal muscles. There's the vein right there. There's the vein. And when this muscle contracts, it gets fatter in the middle. And when it gets fatter in the middle, it squeezes the blood vessel. And that forces the blood to move. So every time you make any kind of skeletal muscle contractions, we force the blood to move. Well, the blood would try to go in both directions. But there's a third helper for veins, and that is those valves. So valves prevent the blood from going backwards. So here's one of those valves. So if I squeeze this vein, blood goes that way. It can't go backwards because the valve prevents it. There's the valve right there. I don't know if you can see it. And there's another valve right there. Here's what the valves look like. They're very, very thin. They're similar to the semilunar valves in the heart. This is the guy who first demonstrated these valves. And he did it very, very simply. If you put a tourniquet around a person's arm and you have them squeeze or pump up, blood fills the veins and you can actually see the valves. Now, nobody knew what these valves were. They saw these bumps, but they had no idea what they were because they didn't have a microscope. Look when he lived. And these things are microscopic. And so nobody had any idea what they were. But he did this very simple thing. All he did was push down and collapse the vein. And then he pushed the blood this direction. Well, the blood tried to come backwards, but as soon as it hit the valve, it stopped. And so this did not fill up with blood again until he removed his finger, and then it filled back up again. So these valves look like this, and they make the blood go in one direction. And so what happens is blood climbs up the veins from valve to valve to valve to valve as you squeeze the veins with skeletal muscles. If you don't contract any skeletal muscles, that squeezing doesn't happen, and blood will collect in your lower extremities. And so your feet will swell and so on. Well, remember, sometimes these valves become incompetent. In other words, they're not working the way they're supposed to anymore. They don't prevent the blood from going backwards, and so it does. And as more and more blood fills up these veins, the veins bulge out, and that's exactly what you see here. And so these are called varicose veins. These are also varicose veins, they're just smaller, but they're due to these incompetent valves. Any questions? So that's where we're going to stop for today. So if you come back tomorrow, we'll try to finish this up completely. We're a little bit behind, and we'll need to catch up. So Antonius asks, do varicose veins hurt? Well, what happens is your legs feel very, very heavy because they're very full of blood. Sometimes you get aching. The aching is due to the lack of blood moving, and so there's low oxygen. And then they swell like crazy because the fluid moves out of the capillaries into the tissues. And they turn blue because they're not getting enough oxygen. And so it's a damaging condition. So over time, it can damage tissues. So I don't know about hurt, but they certainly don't feel normal. Does that answer your question? Okay, so like I said, we're going to stop there. If you come back tomorrow, we're going to try to catch up. I have another collaborate with my other class, so I need to go ahead and end this now. So I'm going to end the recording.